previous lecture, we discussed about large deflection theory for stability analysis by taking an example of single degree of freedom system. We discussed the basis of large theta analysis, which is based on large deflection theory. Before the previous lecture, we discussed stability analysis of different simple single degree of freedom mechanical models by considering small deflection theory. Now we will take two more examples of stability model of 2 degree of freedom system for finding critical load and the mode shape by using energy approach by adopting small deflection theory. Let us first take first 2 degree of freedom system example. This is a 2 degree of freedom mechanical model. We will have to analyze it for finding the critical load. What will be this axial load value P, so that the system will be stable equilibrium, and what load the system will be unstable equilibrium, that we will have to find it out. For analyzing this, we will have to first find out the total potential energy of the system in the deformed configuration. This is the deformed configuration, this is the undeformed configuration. For finding the total potential energy of the system, we will have to first find how much the strain energy stored in the spring. These are the 2 springs. So when it moves, the spring moves, the energy will be stored. So we will have to calculate that. And second part is how much is the external work done. Here you see there are 3 segments of rigid bars and they are connected by pin, and this is connected with the spring. And when this system, 3 bar system, when it is applied with axial load P, when it will get deformed, there will be rotation of this, all 3 segment of bars, there will be rotation. Because of this rotation, this applied load P will move inward, and because of that there will be some external work done. I will just show this example. When the rigid bar, this is the rigid bar, when it is applied with axial load P, when it get deformed, the load P moves downward by certain distance. So this is the delta. So that we can calculate, the delta we can calculate, so that we can find the what is the total work done by the external load. Here this is L, and this distance, it will be L cos theta. This distance will be L minus L cos theta. So this is a example I am showing. When the rigid bar moves by angle theta, the P load moves down by L minus L cos theta. So this delta value is L minus L cos theta. Here we understood when any rigid bar, when it get rotated by angle theta, the load descent by L minus L cos theta, means the work done will be P times multiplied with this L minus L cos theta, that will be external work done. So similarly in this case, if you will see, there are 3 bars, there will be rotation. So for each rotation there will be, the load will be descent, and accordingly we can calculate the external work done. And let us find the total strain energy stored in this deformed configuration. For this we will have to calculate first, this is the energy approach. In the energy approach, we will have to first find the total potential energy of the system. Total potential energy you can calculate as half into KL square theta square plus half into KL square
phi square. This is the energy stored in the spring. This is the energy stored in to spring. Why? Because this delta value is, you can write as L into theta. If the spring is deformed by L theta, the strain energy stored is half K into L theta square. Because of that, the strain energy stored in the spring, this is the first spring, this is the first spring, this is the second spring. In the first spring, the strain energy stored is half K L square theta square, and this is half K L square phi square, because this delta 2 is, you can write as L into phi, and energy stored is half K into L into phi square. So that is written here, first two terms. This is the first term of total potential energy expression. The second term is the strain energy stored in the second spring. And due to the application of the load, there is the external work done. The first, I am writing P multiplied by L into 1 minus cos theta. So this is the external work done because of the first segment of this bar, this one. This is P into L multiplied by 1 minus cos theta, and this you can write here as descent of bar. Let this bar is A, B, this is C, this is D. Then the descent of bar AB will be this. Then you can add the next term minus P into L into 1 minus cos phi. This part is descent of bar CD, and you can write minus P into L into 1 minus cos phi minus theta, and this part is descent of bar BC. If we will simplify this expression of the total potential energy and writing the expression of cos theta as 1 minus theta square by 2, you can approximate it, and cos phi as 1 minus phi square by 2, and cos phi minus theta we can write as 1 minus phi minus theta whole square divided by 2. If this thing we will substitute in this expression of total potential energy, that will come phi is equal to 1 by 2 K L square theta square plus half K L square phi square minus P L into 1 minus theta square by 2, and P L into 1 minus phi square by 2 minus P L into 1 minus phi square plus theta square minus 2 phi into theta divided by 2. This is the expression of the total potential energy of the 2 degree of freedom system, and we will further simplify this. this equal to half k L square theta square plus half k L square phi square minus P L theta square by 2 minus P L phi square by 2 minus P L phi square by 2 minus P L theta square by 2 plus P L theta into phi. And we will further simplify. This phi will be half k L square theta square plus half k L square phi square minus P L into theta square plus phi square minus theta into phi. For equilibrium, this first variation of the total potential energy by del theta into del theta, I am not writing here, del theta cannot be 0, so del pi by del theta equal to 0. Similarly, del pi by del phi is equal to 0. So this is the condition for equilibrium. If we will differentiate this expression pi with respect to theta once and with respect to phi once, we will get the expression like this. If we will differentiate, this one will result k L square minus 2p L into theta plus p L into phi is equal to 0, and if we will differentiate with respect to phi, this will result p L theta plus k L square minus 2 p L into phi is equal to 0. So this is the equation 1 and this is the equation 2. These two equations can be represented in matrix format as k L square minus 2 p L, p L, this p L and k L square minus 2 p L theta and phi, this equal to 0. This equation 1 and equation 2 are two linear equations that can be represented in the matrix format as written, and if we will solve it, we will get P is equal to KL by 3 and P is equal to KL. So these two solutions correspond to two modes of deformation. If you see this equation here, theta is equal to phi is equal to 0 correspond to state of equilibrium for any load P. If we will back substitute in this equation, then we get first one corresponding to load P is equal to KL by 3. If we substitute in this equation, then we get KL square minus 2 multiplied by KL by 3 into L into theta plus KL by 3 into L into phi is equal to 0. This one, if we simplify, this results KL square by 3 into theta plus KL square by 3 multiplied by phi. This will be equal to 0. This implies theta is equal to minus phi. And if we plot the mode shape corresponding to load P is equal to KL by 3, it will come like this. It is a 3-bar system with the hinge point, and this is loaded by P is equal to KL by 3, and it is loaded by P is equal to KL by 3, and theta is equal to phi. For this, it will take a shape like this. Here, this is theta and this is phi. So, this is the mode shape. When the P load P is equal to KL by 3 is acted to this 2 degree of freedom system, rigid body system. In the second case, if we will take P is equal to KL, if we will back substitute in this equation, that will come like this: KL square minus 2KL square multiplied by theta plus KL square into phi, this equal to 0, implies minus KL square into theta plus KL square into phi, this equal to 0, implies theta is equal to phi. And the mode shape corresponding to this P is equal to KL and theta is equal to phi, that I can draw here. This is the 3 rigid bars connected together. This load applied P value is equal to KL, this P is equal to KL, and when P is equal to KL, the shape will be like this. And this is theta and this is phi, and this is, you can write here, this is for theta is equal to phi and P is equal to KL, and for this case it is theta is equal to minus phi and P is equal to KL by 3. So, corresponding to 2 loads, this 2 degree of freedom system will undergo 2 different modes of buckling. For finding the characteristic of equilibrium, we will have to go for second variation of the total potential energy. Then let us find the characteristic of equilibrium. For finding the characteristic of equilibrium, we will have to find second variation of the total potential energy, to theta square, that will be found out if we will differentiate this one, this phi, if we will differentiate, we will get with respect to theta square, which is del square phi by del theta square, if we will do, we will get KL square minus 2PL, and if we will differentiate the total potential energy with respect to phi square, we will get KL square minus 2PL, and if we will do second variation of the total potential energy with respect to theta and phi, that is coming PL. So this is the, let it is the first this is the second, and this is the third. For stable equilibrium, there are two conditions. For stable equilibrium, there are two conditions. Two conditions are to be satisfied. Two conditions are to be satisfied. I wish to mention here, when the system is a single degree of freedom system, there it was only one variable, only theta. That time for stable equilibrium, what we are doing, second variation of the total potential energy with respect to theta, if it is greater than 0, that was stable equilibrium. But for in this case, there will be two conditions. One is del square total potential energy with respect to theta square, it should be greater than 0. This is one condition to be satisfied, and second condition to be satisfied is del square pi by del theta square multiplied by del square pi, del square by del phi square, that should supposed to be greater than del square pi by del theta into del phi complete whole square. So these are the two conditions it is satisfied for stable equilibrium. So these correspond, if in the present problem, the second variation with respect to theta square, we found out how much it is. Second variation is supposed to be greater than 0, then you will have to make KL square minus 2PL should be greater than 0. So here that will reduce to KL is greater than 2P. This is one condition. Or this P is less than KL by 2. And corresponding to this condition, L square into KL minus 2P whole square, it is greater than P square L square, which implies it is K square L square plus 4P square minus 4 KL into P minus P square, which is greater than 0, implies K square L square plus 3P square minus 4 KL into P, which is greater than 0, implies KL minus P multiplied by KL by 3 minus P be greater than 0. So this is the one condition, and this is the other condition. So here, for this to be positive, what is the condition? P should be less than KL by 3. So this is this is the B case, and this is the case A case. If we will consider both equation A and B, both equation A and B will be satisfied if this P is less than KL by 3. Hence, for P is less than KL by 3, the system is in stable equilibrium. And if P is greater than KL by 3, the system is in unstable equilibrium. And therefore, P critical is equal to KL by 3. This is a 2 degree of freedom system. Our objective is to find the load at which the system will be stable equilibrium and when the system will be unstable equilibrium. This is subjected to load P here. This is K and this is 2K. This is the undeformed configuration and this is the deformed configuration. Now, we will have to find the total potential energy of this system in the deformed configuration. For this, we will have to first find the strain energy stored in these two springs. The strain energy stored in these two springs will be half K into Q1 square. The strain energy stored due to the spring, and the strain energy stored in this case here, it is half into 2K multiplied by Q2 square. So, this corresponds to this spring and this corresponds to this spring, this one corresponds to this spring energy stored. The external work done can be calculated by descent of bar AB, descent of bar BC and descent of bar CD. Let me write down the external work done due to descent of bar AB, it is L by 2 into theta square. This we have already discussed. So, if we will find, substitute, this theta is equal to Q1 by L. This theta and Q, and this is L. If you find this theta is equal to Q1 by L for small theta. This is for small theta, theta is equal to Q1 by L. In fact, in the deformed configuration, we have considered the small theta. So, this descent of bar AB equal to L by 2 into theta square, that will come L into Q1 square divided by 2L square. So, that you can write as Q1 square divided by 2L. Similarly, descent of bar BC is L into beta square divided by 2. That will come as L into Q1 minus Q2. This is the relative displacement square divided by 2L square. So, that will be coming Q1 minus Q2 whole square divided by 2L, and descent of bar CD is how much? It is L alpha square divided by 2. This member CD, it is L alpha square by 2, then L into Q2 square divided by 2L square, and this is Q2 square divided by 2L. Now, this is the descent, and if we will multiply with P, we will get external work done. So, if finally if we will add everything, strain energy stored in the spring and external work done because of this descent of bar AB, BC, CD, you can write finally the expression of the total potential energy as half K Q1 square, the second spring, the energy stored in the second spring half into 2K into Q2 square minus, if we multiply with P with this descent, we will get the external work done, and if we take the common P by 2L, we will get Q1 square plus Q1 minus Q2 whole square plus Q2 square. So, this is the total potential energy. If we will be simplify this, pi implies pi is equal to K by 2 minus P by L into Q1 square plus K by minus P by L into Q2 square plus P by L into Q1 into Q2, that we can write it. This is the expression of the total potential energy for equilibrium. For equilibrium, the first variation of the total potential energy is equal to 0, and that we can follow it, that first variation of the total with respect to first Q1 with del Q1 is equal to 0. This is one, and second is del pi by del Q2 into del delta Q2, this equal to 0, and this correspond to implies del pi by del Q1, this is equal to 0, because this delta Q1, this cannot be 0, only del pi by del Q1, that will be 0, and which will be, if we will differentiate the total potential energy from this expression, that will get K Q1 minus 2P Q1 divided by L plus P Q2 divided by L, this equal to 0. And if we will simplify this, Q1 into 2P minus KL minus Q2 into P equal to 0. This is let equation 1. And if we will follow this expression, that is del pi by del Q2, this equal to 0, as delta Q2, this cannot be 0. So, this implies minus P Q1 minus Q2 into 2KL minus 2P, this equal to 0. This is second equation. These two equation, if you write in the matrix format, this will be 2P minus KL minus P, this is minus P into minus 2KL minus 2P, and this is Q1 and Q2, this equal to 0. And this is a eigenvalue problem, and this Q1 Q2, if it becomes 0, this is the trivial solution. For non-trivial solution, this coefficient matrix to be 0. So, you write for non-trivial solution, the coefficient matrix will be 0. If you will find the determinant value, if you will equate to 0, this becomes 3P square minus 6PKL plus 2K square L square, that will be equal to 0, implies P is equal to 0.4226 KL, or it is 1.577 KL. So our objective is to find, for corresponding to this load, we to need find the mode shape. Substituting this P is equal to 0.4226 KL in the equation, any one equation. Let us will substitute in equation 1. If we will substitute it, how much in this equation? If we will substitute, the value P is equal to 0.4226 KL. If we will substitute in this equation, that will come as Q1 0.8432 minus 1 minus 0.4226 Q2 is equal to 0. This implies the solution of this Q1, Q2, these are dependent. We cannot independently, we cannot find the value of Q1, Q2. So Q1, if this Q1 value is equal to 1, then Q2 value will be minus 0.371. And this corresponds to the antisymmetric mode of buckling. How it will be? This corresponds to, you can write here, antisymmetric mode, and if I draw the mode shape here, this is the 3 rigid bar systems, and this is loaded by the load P here, and this is loaded P. This P is equal to 0.4226 KL, and it will take a shape like this. And this value is Q1 will be 1, and this Q2 will be minus, this is in other side, so minus 0.371. This is not drawn in scale, but this is the shape, mode shape, which correspond to load P is equal to 0.4226. So let us find the mode shape corresponding to the other root of the equation. Other root of the equation was 1.577 KL. If similarly substituting this P is equal to 1.577 KL in equation 1, the same equation, if we will substitute, then we will get, let me write down the equation, Q1 into minus 1.577 plus 1.154 Q2 is equal to 0, implies Q1 minus 0.7317 Q2 is equal to 0. And the corresponding to this these two equation, if we will solve, this results Q1 is equal to 1 and Q2 is equal to 1.366. So this correspond to the symmetric mode of buckling, symmetric mode of buckling, and the mode shape will be, let me plot the mode shape. And this is one bar, this is second bar, and that will take a shape like this, this is and this one is this Q1 is equal to 1 and this is Q2 is equal to 1.3666 and this correspond to P is equal to 1.577 KL.